In the previous video, we saw how all simple harmonic motion can be modelled by the equation the acceleration is proportional to the displacement, but in the opposite direction. And we saw how the general solution for this is a trigonometric function. However, that is a little bit unrealistic in a lot of circumstances because that would be suggesting that the amplitude of oscillation is always constant. So that would be suggesting that our pendulum is going to be back and forward forever, going back and forth to its maximum amplitude, going forward and back and forward and back, always, never decreasing in amplitude. Similarly with a mass on a spring, going backwards and forwards forever, never decreasing its amplitude. And in reality, we know that there's going to be some resistive forces. We call them damping forces. So we need to include these in our mathematical model. Now we know that all resistive forces, whether we're talking about friction, whether we're talking about air resistance or heat or whatever it is, we're talking about frictional forces, and we know that they will be proportional to the velocity. The higher the velocity, the higher the frictional force. The higher the velocity, the higher the air resistance. Therefore, I can improve my model here like this. We can see that the first bit is exactly the same as I had before, the rate of change. The acceleration is proportional to the displacement but in the opposite direction. And then I've also, the acceleration is going to be decreasing by this frictional force where it's proportional to the velocity. This is what we call our restoring force. This is the force that was forcing my pendulum to go back to its equilibrium position, or it's the force constant of the spring making the mass go back to its equilibrium position. So this is why it's called the restoring force. It's restoring it to its equilibrium position. And this is the damping force term here. Now I can obviously then move all of these terms over to the left-hand side to get my more up-to-date, also not up-to-date, more refined formula for damped harmonic motion. And we can start to come up with a general solution for this, because the auxiliary equation will be that, m squared plus km plus omega squared equals 0. And we're going to consider 3 different cases of this. So first case, what if this auxiliary equation had distinct roots? So the discriminant of this, so b squared minus 4ac, so k squared minus 4 times 1 times omega squared. What about if our discriminant was positive? That would mean there's 2 distinct roots, and our general solution could be written like this because we've got 2 different roots. In that case, we would call it heavy damping, and in that case there would be no oscillation whatsoever. We wouldn't get the oscillating over time. The system would just go straight to its equilibrium position. If there was repeated roots, so if the discriminant equaled 0, then we would have 1 repeated root, and as we've seen previously, that would then give me a general solution of that form, and we would call that critical damping. In that situation, again, we wouldn't have any oscillation, but it would be on the point of oscillating. So that's why it's called the critical damping. It's on the very point where you're about to start getting oscillation. And then the third solution is, what if there were no real roots? If there are no real roots, then we know that the discriminant is less than 0. And in that case, we know that we can write down our general solution in this form. And now we will start to get some oscillation. There will be some light damping caused by this term here, but we would get some oscillation. So you can see here that the amplitude is decreasing over time because of this exponential function here. Now, it might seem like these 2 situations here are very similar. What I'm going to do is I'm going to copy a link to a different YouTube video, an experiment that somebody's done underneath this, where it shows that it's a ruler oscillating with a magnet on it, and the magnet is providing the damping force, and it's a short experiment showing the different cases here. So I'm going to link that. Make sure you watch that. It's about 3 minutes long, so that you can see clearly the difference between light damping, critical damping, and heavy damping. And so you can visualize that, because I know it's not particularly easy to visualize the difference between these just by looking at them. Let's look at an example. Now we're going to introduce another factor into this as well. As well as damping, we're now going to introduce the idea of forced harmonic motion. So what this means is we have now got an external force that's adding to the oscillation. So whether that's so if we're talking about a pendulum, it might be a force pushing the pendulum every period, like that. That could be an external force. It's helping the pendulum move. So forced harmonic motion is where you have an external force that's adding to the oscillation. And that will look like this in this case. So we've got our acceleration. This is our damping force. This is our restoring force. And this over here is what we call the driving force, because it's adding to the oscillation. It's forcing it to oscillate. So let's have a look at an example that's putting all of this together. It's going to be quite a long example. That's why I wanted to do forced and damping together. So we have a particle of mass 1.5 kilograms is moving on the x-axis. 3 forces are acting on the particle. A restoring force of magnitude 7.5 x newtons. So we can see here that it's proportional to the displacement. A resistance force of magnitude 6 v newtons. So again, we can see that's proportional to the velocity. And it has a driving force of magnitude 12 sine t newtons. Initially, so that means when t equals 0, x is 5 and v is 2. And we need to show that d2x by d8t squared plus 4dx by dt plus 5x is 8 sine t. So we need to show where this equation comes from. So we need to basically combine the 3 forces we're given to give this equation relating the acceleration. So I'm going to start off with Newton's second law. So we're going to start off with force equals mass times acceleration. These are the other 2 bits of the question we'll come to later. So force equals mass times acceleration. So what forces are acting on this particle? Well, we had the restoring force, the 7.5x, and I know that's always in the opposite direction to the acceleration. So hence why I put a minus 7.5x. Then I've got the resistance force of 6v, and again I know that that is always going to be negative because it is by nature a resistive force. So I've got minus 6v, obviously writing v as dx by dt here because this is the equation I want to get. I want to get an equation in terms of x, not v. So I've got my restoring force, I've got my resistance force, and then we've got the driving force, which is a positive value because that's going to be adding to the acceleration here. And that's equal to the mass, 1.5, times the acceleration. I've then divided both sides by 1.5, and now move all of this to one side of this equation to get this, which was what we wanted to show in part A. Part B said find x as a function of t. So we want to solve this equation now. So my auxiliary equation to the left-hand side here, so making it equal to 0 to begin with, is this. The two values of m will be -2 plus I and -2 minus I. These are the two solutions to that auxiliary equation, which I know then gives my complementary function to be e to the -2t plus a cos 1t plus b sine 1t. So this is my complementary function. I then need to find my particular integral, because this is a non-homogeneous equation. So because it's an 8 sine t there, I'm thinking that my particular integral is going to be x equals p sine 1t, and it's a 1t because it's a 1t here, plus q cos 1t. Remember that whenever you have a trigonometric function, you need to have a combination of sine and cos in your particular integral. So I am going to substitute this into the left-hand side. To do that, I need to differentiate it twice. So differentiating this once gives this. Differentiating it again gives this. Now substituting this into here, and this into here, and this into here, gives this long line here. Collect up the like terms. So collecting up the sine t here, the sine t here, and the sine t here gives this. And then collecting up the cos t here, the cos t here, and the cos t here gives this. And now comparing the left-hand side and the right-hand side, I can see that here I've got 4p minus 4q. 4p minus 4q, and that has to equal 8 because I've got 8 sine t on the right-hand side. Sorry. Collecting up the like terms here, I get 4p plus 5. So that's not right. That should be 4q. 4p plus 4q, and that's going to equal 0 because I should have 0 cos t on the right-hand side over here. And then solving these two equations simultaneously. Solving these two simultaneously gives p is 1 and q is -1. So I know my particular integral looks like this. So this was my complementary function. This is my particular integral, so I can now add those two things together to get my general solution. I now need to use my boundary conditions to get to be able to work out what the constants are. So my boundary conditions, I was told that initially t is 0, x equals 5, and v equals 2. So let's use those boundary conditions. Let's take my general equation and substitute t is 0, x equals 5 into that. So 5 in here, 0 in here, 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 and here. Gives all of that. Which obviously, that's 1. That's just going to, cos 0 is 1, so that's a. That's 0. That's 0. That's 1. So I just get 5 equals a minus 1. Therefore, a is 6. Now I'm going to use the second boundary condition, which remember was saying that when t is 0, the velocity was 2. So to use this, I need to differentiate this to get my velocity function. So differentiating all of this through, I'm going to have to use the product rule on this first part. So differentiating this first gives this, times in by this, plus this times the derivative of this, plus sine differentiates to cos, and minus cos differentiates to sine. So this is my velocity equation. So substituting 2 here, and then 0 here, 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 and here, gives all of that. And then just going through and simplifying, because we know that cos 0 is 1, sine 0 is 0, that's going to be a 1 there, that's going to be a 0, that's going to be a 1, 1, 0, that's obviously just going to be a 1 there at the front. Going through all of that now, and now we know that a is 6, so that allows us to work out that b must be 13. And there we go. We've answered part B of this question, which asks us to find the general solution. Sorry, not the general solution. It asks us to find x as a function of t, which is exactly what we've done here. We've found x as a function of t. Finally, part C. Describe the long-term behaviour of the mass. So long-term. So that's suggesting what happens as t becomes a really large number, as t tends towards infinity. So as t tends towards infinity, I know that my exponential will tend towards 0, because we know that the e to the minus will look like this. And as t gets bigger and bigger, this gets smaller and smaller and will tend towards 0. Which means that if this tends towards 0, then all of this will tend towards 0, and my x function will just become sine t minus cos t. And if I want to describe this, and I do want to describe it, that's what the question's asked me to do. It's asked me to describe the long-term behaviour. So I can say that that's the equation, but that doesn't help me to describe it. To describe it, I'd like to say what its amplitude is eventually going to be and what its time period is eventually going to be after all of this has died down. So I want to rewrite this in this form. So just going through those usual steps of regular A-level maths, rewriting, so comparing this, and that's telling me that I'm going to have a sine t minus cos t. That tells me I need to have a minus in the middle here. Matching up, so expanding this out, comparing this and this, I can see that r cos alpha is going to be 1. I can see that r sine alpha is going to be a 1 as well, because the minus is already there. Divide through, draw my little triangle. So I find that r is going to be root 2, alpha is going to be pi over 4, which allows me to rewrite this in this form, which finally now allows me to say, after a long period of time, as t tends towards infinity, the motion will become simple harmonic motion, and it will have an amplitude of root 2 and a period of 2 pi, because I can see here that omega is 1, so the time period would be 2 pi over 1, which is 2 pi. That's where that came from. There we go. I have described the long-term behaviour of the mass. So key things then really is, this is your equation for damping, including this extra term, and then if we have an external force that's adding to the oscillations, then we can include that over here as well.